Great. So we should probably get started. I think it's about noon on the hour. Thanks for coming out here and having your lunch here. And of course, thank you so much for coming to PDC. I know a lot of you have traveled a long way to get here. I know for all of you, it's a significant expense to come out here. So thank you. I'll introduce myself first. My name is Max Feingold. I'm a development manager on the messaging platform and services team. And what we do is we work on frameworks that make it easier to build scalable services. So I'll start by telling you a little bit of a story about why I'm here. So long time ago, I was in college, and I wrote my first web service. It was actually the first real program that I'd written, so it's kind of like first love in some ways. It was a turn-based web game. It was about spaceships and planet battles and fleets and things like that. And it used what I considered, of course, at the time to be the pinnacle of all technology, web forms and GIFs. I wrote it in C++. I had a custom HTTP server, a custom database, wanted it to be fast. And multi-threading was fashionable at the time. So I used all the synchronization primitives, critical sections, events, mutexes, semaphores, whatever I could find. And so with all those locks protecting my state, I'd start running into deadlocks. That's kind of what happens. So I carefully studied my lock acquisition order. As I recall, I wrote it down. It's like a page of text to get it all straight, which lock to take first, what order. And so my code essentially assumed that I could just stop the world at any point in time, and I could get exclusive access to any of the data in my program. And this gave my program a bit of a small flaw, which is that it really only ran on a single machine. So I had about 20 users at the time. They logged in, played the game. It was on a 486 on the campus network, so it could handle the load. And so I was lucky in a way, because if I had had more users, I would have had to rewrite that game. So, let's master this technology. So what's this talk about? So we've developed some really great cloud services all across the Azure platform. And we're going to serve millions of users. Eventually, we're going to serve billions. And so because of this, we've had to design our services to scale from the ground up. And so this talks about sharing with you what we learned along the way, how we think about scalability, what challenges we faced when building scalable services, what's the architecture behind what we did, what are the principles, what are the patterns, what are the rules of thumb. And also, I'm going to give you a glimpse into how the .NET framework is going to evolve over time to make it easier to build scalable services. Now, this is largely an architectural talk. Don't expect lots of demos or any specific APIs. I'll try to keep you awake over this time by giving you some real-life examples from the Azure services and how they scale out. So apologies to poetry and real poetry. These are the haikus of scalability. So I couldn't fit in a line about cherry blossoms in the spring. I did try. But you'll see these themes show up throughout the talk as some of the key principles and patterns that enable us to build scalable systems. So what you can see here is the operations model that we use. It considers machines to be nameless and disposable. You can see state management with caching and loose consistency and relaxed isolation. You can see redundancy, partitioning, loosely coupled messaging, best effort, message loss, retries. And you can see software that self-monitors and self-heals, is designed to expect failure and to continue to work seamlessly, even in the face of failure. So here's the agenda, quick roadmap for the talk. I'll give you a quick introduction to scale out. I'll walk you through scaling out an example service. I've chosen the workflow service for this. And I'll take you on a deep dive into the routing and data overlay, which is a framework that we're building that makes it easier to build scalable services. I'll give you an overview of some of the Azure services and what they did to scale out. And then I'll talk about one of the interesting side benefits of scalability, which is the operations model that I alluded to earlier. And then, of course, we'll recap and get some time for Q&A. I know some of you may have flights that you need to catch, so I'll try to finish this out on time. So today's Thursday. You've been here at the PDC for 4 days. I hope I don't need to sell you on this. So if you have a single machine, if you're building services that run on a single machine, typically you face two challenges. You need to handle load, and you need to be available. And eventually, with a single machine, you'll have more users than the biggest machine you can afford. Or it might turn out that there is no bigger machine. And of course, you have your single machine. Eventually, you have to take it down at some point, in which case your service won't be available. And so eventually, you have to add more machines. There's really no way around it. You have to scale out. So for developers, this really gives us an interesting challenge, which is how do we write the software that runs on multiple machines while remaining just as correct as the software that we know how to write for a single machine? Now, a lot of the concepts that we use to answer these questions, they're actually as old as the hills. They've been around for a long time. So one classic example is a simple web service. Web servers use redundancy to address availability and load. They copy files around. They do round-robin routing to any of the machines that has the files. It's basically stateless scale-out. There's no state retained between messages. It actually works really well. Another classic example is DNS. So DNS uses partitioning. It uses replication. In fact, it replicates across the entire internet, across the entire world. And it does that to address, again, availability and load. It also takes advantage of synchronization latency. And it embraces a concept that we call eventual consistency. And I'll talk more about that in a bit. So as an example, you've probably updated your IP address at some point with your naming provider. And you've probably then sat down and waited and waited. Maybe you waited a few minutes, a few hours. In the old days of the internet, it would actually take days in some cases for your ISP's name servers to pick up that new address that you had just stored at your naming server. And this seems like a flaw, but it's actually by design. The eventual consistency that's being used here is what really allows DNS to geoscale the way it does. You can imagine how difficult it would be to take every DNS server on the planet and run some kind of distributed transaction that would update every DNS server at the same time with the same data. It just wouldn't work. And so the scale-out approach that I'm going to talk about here really ends up combining the best of both of these systems. It makes use of redundancy. It makes use of statelessness wherever possible. And it also uses stateful partitioning where needed. And of course, it makes use of eventual consistency. So let's take a bit of a bottoms-up look at what kind of the generic architectural stack might look like for a scalable service. So of course, we build on a foundation of commodity hardware, a bunch of machines. And we may use virtualization, of course, to abstract away the hardware, get better utilization, use CPU and memory more efficiently. We also self-assemble. Because at scale, machines need to be self-assembled in order to be manageable. So the abstraction that this layer presents to the service is really that of a quantum sea of machines. The machines appear when they're needed. They disappear when they're not needed. They'll boot up, provision themselves with the right software, join a service, and effectively start handling incoming work. Now, services themselves are usually composites. You usually don't build a single service. You build them of smaller, independent, composable services. Each composable service is usually built from tiers. That simplifies the architecture, and it successfully separates out roles. So here I have the communications tier, which is your classic front end, which will speak protocols. It'll manage sessions. It'll do throttling, access control, security, all those things. Then there's the logic tier, which is the heart of the service. Really, it's what makes the service unique. It's the service-specific business logic. And then there's the storage tier, which is where all the persistent state is stored that the service uses. In turn, each tier is partitioned, and that provides redundancy and load balancing. Now, how to partition and store state in an efficient way is actually where most of the interesting challenges of scalability come in. And that's what I'm going to probably spend virtually all of this talk discussing. So an example of this kind of architecture is a service you're pretty familiar with, which is Hotmail. Hotmail is an email service. It has some front-end services that like login, redirection, and of course the HTML presentation layer that lives in the communications tier. It has a logic tier that pretty much does what you'd expect. It hosts the mail delivery services, incoming mail, incoming spoolers, outgoing spoolers. And it turns out most of the CPU time in Hotmail is spent processing spam. So that was an interesting data point that I found. Then there's the storage tier. It hosts the Hotmail user storage, messages, attachments. And of course, it's heavily partitioned. It's partitioned by user. And data is replicated across multiple drives to avoid losing data. So that's one example. Now let me take a step back and define a few things first, a couple useful concepts for the talk. The first is consistency. So consistency is a concept that relates to state management. And the question that consistency asks is this: how soon do readers see data when data is changed by a writer? Seems like a simple question. There's three types of consistency. The first is strong. And the answer to when are changes visible is now, immediately. That's because we use synchronization to provide strong consistency. A classic example of strong consistency is, a program that launches missiles. In that case, you really want to make sure that where the missile is being launched when it's getting launched are in sync, synchronized. There's no stale data in the system. If we were to consume stale data and send that missile to the wrong place, our program probably wouldn't be correct. So there's programs that need strong consistency. There's also programs that can handle eventual consistency. And eventual consistency occurs when a change is made. Readers may see that change eventually, but sometime in the future. It may not happen immediately. So you can be a reader and you can read stale data for a while. Classic example of this is changing your address. It turns out most of life is eventually consistent. At the very least, the speed of light limits the degree to which changes can propagate throughout the world. But going back to changing your address, you buy a new house, you go to a new location, and you have all this mail that was coming to you to the old address. You change your address, you contact your bank, you contact your credit card company, update your address, all the new mail will be sent to you at your new place. But what happens to the mail that went to the old place? Well, this is an eventually consistent problem. And so the mitigation we have is to use the Postal Service. We file a change of address form, and the Postal Service will redirect our mail to the new address until it doesn't need to anymore, because all of the writers have been updated with that data. You can imagine doing something very similar with DNS, actually, where your old IP address can get updated to essentially forward to the new IP address. It's exactly the same thing. And then there's optimistic consistency, which is kind of like eventual consistency, except you're not sure whether the changes will stick. They might or they might not. Classic example is a stock ticker, where you may not necessarily need exactly the right value at exactly the right time, because you'll get the next stock quote in a minute or in a few seconds. And it's actually fine to drop packets and not actually see that one update. So that's consistency. The other concept that's going to be useful for this talk is message assurances. So you probably already know this, so I'll kind of go over this quickly. There's 4 kinds of message assurances. It goes all the way from exactly once, where we have no losses and no duplicates in the system, to at least once, where we have no loss, but we can handle duplicates. So that's your classic retry scenario. Sending email is a pretty standard example of this, where you send an email, you don't receive a response. What do? You send another email, and so forth. There's also at most once, where we can tolerate message loss, but we don't want to see any duplicates. And a pretty standard example of this is streaming video, where if you drop a frame, great, just pick up the next frame and keep going. But receiving that dropped frame a minute later actually has no value at all, so you never retry. And then there's best effort, which essentially has both loss and duplicates. And just like with consistency, just like life is eventually consistent, it turns out life is also best effort. And you'll see some examples of that. So let's get a bit more concrete here. And let's talk about how we'd actually design a service to embody the general architecture that I just showed you. And as I said, I'll use the .NET Workflow Service as an example of how you would go about building a scalable service from the ground up. It turns out we've had, as you know, we've had a great workflow runtime in the framework since .NET 3.0, actually since the last PDC, if you were here. We also have the .NET Workflow Service, which we've announced. If you've been to some of the talks and keynotes, you've probably already seen a bit of it. And the Workflow Service is a scalable cloud service that hosts user-written workflows. And so the Workflow Service gives us a really great bottoms-up story that we can tell, where we can basically look at the experience of 2 developers. We can look at the infrastructure developer, the one who builds the service and has to scale up the workflow infrastructure to provide a host. We can also look at the application developer, who develops workflows to run on top of that service, and see what happens to them when they enter this scalable world, and what do they experience. So I'll start with the infrastructure developer. Now, of course, the challenge here is you're given a framework. How do you design that scalable workflow host? So, well, you'll probably write a custom host. If you've written workflow programs, you're pretty familiar with that already. It'll probably run on a single machine. That's where you start. You have incoming messages, so you store them in a queue. And you have a database where you store your instance state. And you'll probably use transactions to pull messages out of the queue, update some instance state, store it in the database. You get exactly once semantics. It's actually a really great solution. It's simple, and it's affordable. And it doesn't take a whole lot of effort for the operations model. It doesn't take a whole lot of effort to keep it running. Now, of course, there's a small flaw in this kind of architecture, which is that it's not going to scale. Eventually, load is going to increase to a point where it's going to overwhelm any single machine. And so there's no real choice but to build some scalable hosting environment and to run on multiple machines. So before I continue, I wanted to give a plug. This is actually one of the forward pointers that I can give. since today's Thursday. So there's a talk at 1:45. It's Mustafa Ahmed's talk on the .NET Workflow Service. If you're interested in this stuff, you should really go. It's a great talk, and certainly recommend it. So where were we? Right, so we were throwing machines at the problem. So where do we start? Well, let's partition the logic tier. We can divide up all the computation work there. And really, the best way to partition workflow, it's actually really easy. We can divide it up by workflow instances. We can pin specific workflow instances to specific machines. And what that gives us is processing locality, which is a really great thing in these scalable environments. Because multiple messages that come in will land at the same machine that has the same state. It's running in the same memory chips. There's no need to duplicate it, load it in, load it out. It's just there. You can run the message, process the data. Great. And so turns out you can actually scale out the storage tier in precisely the same way, just partition it out by instance. So that's a pretty good solution. Your communications tier is now scaled out. It's not just kind of a little firewall anymore. And it needs to keep up with this. So it needs to figure out how to correlate those incoming requests to the right place in the middle tier, in the logic tier. And so it probably has some configuration that maps things around. It's actually pretty simple. Now, one thing you'll notice, though, and this is a pretty good solution for deployments of a single size, certain size. One thing you'll notice is that running this solution, managing all those machines and keeping them up to date is actually a chore. It's work. Because each workflow, for example, has its own connection string to the database. So you're going to have to maintain these individual configuration files, roll them out, update them. Also, adding and removing machines, because you want to be able to do that. It's going to cause configuration changes in the communications tier, because it was routing messages around. And so as load increases, and as you add more machines, you end up with more of them than you can actually manage efficiently. And at this scale, something else happens, which is that the probability of a machine failure, of hardware failure, even if the software is perfect, the hardware can fail. And the probability of it failing goes up pretty dramatically as you start scaling out. And when something fails, it's an emergency. Pagers goes off, and your administrators are off to the races to repair that broken system. And so they need to work really hard. Eventually, you may have too many machines for them to handle in a really efficient way. So really at high load, what you want to do is you want to build a system that's easier to operate, and it gives you just higher availability from the ground up. You need to design the system also around the reality that hardware can fail and machines can fail. So it's not just theoretical. I've seen data from Hotmail, for example. Turns out 5% of Hotmail's disks, their hard drives, fail every year. Now, that actually doesn't sound like a whole lot, or at least that's how I reacted, because I actually do worse at home. Not sure about you. But it turns out at the scale that Hotmail runs, they have a lot of disks. It turns out that's about 30 disks per day that are going down. And so that's 30 times that pager is going to go off. It's 30 emergencies if they build their software the wrong way. And so, of course, machines in the communications tier can fail here. What do we really want out of that? Well, that should really only affect the sessions that they're maintaining to the outside. They should be stateless otherwise. That would be great. Machines in the logic tier can fail. And really, that should only affect the active work that they're doing. And it really should only affect it temporarily. So as you can see here, we can replicate message queues. And I'll run through the little replication animation. So that machines in the logic tier can fail over. And the message queues that they were maintaining can fail over too. That's a great solution. Machines in the storage tier can fail as well. Now you can replicate state there as well. And you can also, while you're there, you can provide an abstraction to kind of unify the connection string management that we talked about. So at this point, we've got this storage tier. And it ends up looking like a scalable storage service. It's not just a heap of SQL machines anymore. So this is actually getting pretty interesting. It's a bit sophisticated. And there's some challenges to implementing a system like this. So for example, how do you keep the communications tier completely stateless, but also know where to route those messages when they come in? They need to go to a specific place. How do you route? Also, how do you change the topology of all of these tiers without having to update configuration and jump through a bunch of hoops? That's a problem. It may not be a problem for developers, but it's a problem for administrators. And we need to build software that makes the life of administrators easier. In fact, at scale, that's actually one of the most important jobs we can do as developers, which is to make that experience, the experience of the IT pro, much, much, much better. So later in the talk, I'll do a bit of a deep dive into the overlay technology that we've built. It actually ends up answering some of these questions. So something else happened while we were making our service highly available. It turns out when you embrace these machine failures and you designed accordingly, you lost that exactly once world that you started with. You were using distributed ACID transactions in the first two scenarios. The problem is using transactions isn't quite the right design point for a machine at this, or for a system at this scale. And one reason is replication. I just mentioned that. It's a great, useful pattern. It does mean that you have multiple copies of your data floating around. You may have 2, you may have 3, you may have many. So which is the truth? Which is the right one? Maybe all of them. Great, so how do we keep them synchronized? Well, you could use transactions, maybe. The problem is, transactions assume that machines come back. Transactions assume that disks recover, that transaction logs recover. And transaction protocols, two-phase commit, blocks until all of those transaction logs, all of those machines come back. And so in this world, we've just accepted that machines go away. Disks can permanently go away. And really, they can do that at any time. So really, at this scale, the state management pattern that you want to start thinking about is a lot more loosely coupled. You might think about compensation, for example. Take compensating actions instead of the big abort switch. Also, at this scale, the default messaging pattern is best effort. So between services, across services, you'll be using transports like HTTP. You'll be using transports like REST, probably like the .NET Service Bus. And these aren't transacted transports. They don't give you exactly once semantics. They're best effort. So you get a trade-off. You can take the message loss, send, and nothing ever happens. Or you can do like email. You can send, send again, send again. So you'll retry messages. It's pretty obvious. You'll retry any message for which the send actually matters, and many will. This also means that everyone is retrying. So you have to tolerate duplicate messages. You have to be idempotent. And this is yet another pattern in this world. So at this scale, the dominant pattern that you find is really this loose coupling. There's loose coupling for state management, and there's loose coupling for messaging. So take a break here. So you just built a scalable system, and you're starting to kind of explore what the consequences are. So let's see what actually happens here. So you started in a world where you had shared state. You had a global truth. You had a single consistent store. You also had ACID transactions, and they gave you isolation. There you go. They gave you isolation. They gave you concurrency control. They also gave you strong consistency, the ability to abort and return to a known state at any time, which is actually super useful. You had exactly once messaging. You used transactions. You used stateful messaging protocols, like WS Reliable Messaging, to ensure that exactly once delivery. Also, machine loss was a catastrophe. And like all catastrophes, you don't write code for it. You left it to the administrator to handle that problem. You also kept your processes running always. You only have one, so you'll probably want to keep it up. So you might do things you might feel a little bit bad about, like catching those unhandled exceptions and things like that. Just keep it running, keep it running. Maybe it degrades, but keep it running. So in the scalable world, we've got some counterparts to all this, of course. First, we have partitioned and replicated state. You keep multiple copies of your data. You exploit locality. You make decisions based on local truth instead of global truth. You also have eventual consistency. You have relaxed isolation. You have caching everywhere. You might want to get comfortable processing stale data, for example. And you might want to compensate instead of aborting. Also, you have loosely coupled messaging. Best effort, you expect message loss. You'll retry, and you'll be idempotent. You'll detect duplicate messages. And operationally, you need to design to make sure that machine loss is just business as usual. You assume that machines, disks, any local state that you have can really just disappear at any time. Addresses, the names of machines, can be totally volatile. They're transient. And this, you accept. Lastly, instead of keeping our process running at all costs, we have recovery-oriented computing. And so you embrace the principle that it's better to fail quickly and fail safely than to slowly degrade. You self-monitor. You verify your invariants. You check the stack underneath you, make sure it's working correctly. You have runtime assertions. And you fail fast. You fail safe, even on suspicion. You also have an aggressive recovery model, where you restart the process if something's going wrong. You reboot the OS if that doesn't work. If that still doesn't work, probably replate the machine, reimage it. And if that still doesn't work, you yank the machine out and you replace it. And none of these are catastrophes. None of these are actually unexpected. They're just part of life. So even after all this, you might not yet be a believer in loosening consistency requirements. So as developers, we're taught from a pretty young age to seek the truth, and avoid stale data, because stale data could go bad, and you wouldn't want that. And so back in college, I remember writing my game, writing some of the more sophisticated parts of it. Actually, the hardest part was writing the code that did a turn, that did an update. And it turned out every time I'd do that, I'd move spaceships around, and I'd run fleet battles, and the populations would change of the planets, and the resources would change, and some planets might actually get destroyed. You get the idea. And the only way I could really figure out how to make that work was to take that giant lock in front of this code and then do all of the things that I needed to do. And it could take seconds, or it could take minutes, or, well, that's about it. But it could take a long time. And in the meantime, my users sitting there on the network, F5, F5, F5 in their browser, just waiting for that map to come back, waiting for the state to come back so they could play the game again. So there's a trade-off that you get between the strong consistency world of taking a giant lock and doing some stuff and actually making your service available. And this is the sort of thing that just gets worse as the size of the world that you're modeling in your software gets bigger. So coming back to planet Earth, you could be modeling business systems. And it's really important to remember that the software that we write for these systems, it really only simulates reality. It's not reality itself. It's not the truth. So take a car dealership, for example. It has a real inventory of cars out there somewhere in garages and warehouses and such, on boats. Then it has an inventory table in a database with some numbers and some counts and some names and such. And it's worth keeping in mind there are real cars. Well, okay, maybe not that one. There are real cars out there. The cars do represent the truth of the world. So we, as developers, we don't have cars to work with. We have the inventory table. So you could be developing a dealership service. Your first instinct, just like mine was back in the day, is probably to sacrifice just a wee bit of availability to make sure that all uses of that inventory table are just totally consistent. So you're reading the values in the inventory table. You take a read lock. Hold it until you've read it, release it. Let's say someone's buying a car. You check that inventory, you decrement it, but only when it's done, and it could take a while for the car to be, check a credit card, get some credit financing, all those things. It could take a while. And you'll probably hold that write lock until it's done because you don't want to mislead people. Could be terrible, right? You could sell the same car to two people. That would be bad. Race conditions are bugs, right? This we know. So I'll tell you a story about a friend of mine. Actually a long time ago, he was buying a car in Houston and purchased a Honda, did kind of one of those custom detailing kind of work. Turned out they had to ship the car from Japan, so it took 3 weeks to get the whole thing over. And so the car arrives, and it's in the garage. They're detailing it, fixing it up, and so forth, and it's ready. Turns out that was the day that Hurricane Alicia blew through Houston, and the garage, that had the car, it collapsed. And so the dealership, they call my friend the next day. They're sorry. Right? So it turns out the car is under 6 feet of rubble. There's a few options. He could get another car, different car. He could get a better car, of course, because he'd upgrade. Or they could ship another car from Japan, and it'll take a few weeks and such. So, but they were sorry. And that's actually kind of important, because for the dealership, it turns out selling the same car twice is actually the same as this. You call the customer. And you say you're sorry, we'll make it up to you. And it's actually totally fine. So it turns out that every real business has a business process that knows how to apologize. We all do that. And it doesn't run a whole lot. It doesn't run very often, but it's there. And you can use it. And so knowing that you have it actually gives you a really interesting way to think about some of those race conditions that occur inside your program against, say, 0 inventory items. It could be that maybe it's okay to apologize when you have those race conditions. And actually that may be fine. Maybe you don't have to display exact counts. Maybe you can make sales decisions based on data that's a little bit slightly stale. You might have to apologize just a little bit more often. But it turns out you've already written that code. Great. So this is what Pat Helland, our friend Pat Helland, calls apology-based computing. I've talked about inventories here. But really this reasoning, you can use this reasoning for any kind of data. And there's a principle here, which is that at scale, truly at scale, getting global truth is really, really expensive. And that's why the haiku says you can't afford the truth, because you can't. So use local truth when you can, because that's what's going to help you scale. So I've told you about about the infrastructure developer and some of the challenges the infrastructure developer faces when building some of these systems. There's some new challenges. There's a few new concepts. What if you're an applications developer? You may not build a whole lot of infrastructure. So how does this end up affecting you? So to start with, the app developer, turns out, needs scale for exactly the same reasons that the infrastructure developer does. Your service becomes popular. And so you need to handle more load. You need to be more available. Now, eventually, you want scalable hosting. You want to be scalable. And you could have it either on-premise or you could have it in the cloud. Either way, the question becomes, what happens to your service? What happens to the code that you wrote when you go and port it to scalable infrastructure? Now, ideally, the answer would be, well, nothing. It just works. Probably not going to be the case. As a rule of thumb, the higher level the framework that you're using, the more portable your service will eventually be. So for example, you've seen Windows Azure, you've seen the workflow service. Workflow and ASP.NET are great examples of frameworks that you can use today that give you a great experience on-premise. But they also have dedicated cloud hosting in Azure. And so in both cases, the abstractions you get, the experience you get, the APIs you get are the same or similar on the premise and in the cloud. And so this is actually the goal that we have, that Microsoft has across the board for the Software Plus Services developer experience. So first, we offer a choice of programming models. It's just like in the frameworks today. You get a variety of choices at different layers of abstraction, different languages, APIs, and hosting. And you'll also see steps towards unifying that programming model for cloud and premises. So as the platform evolves, we want it to be the case that targeting the cloud or premises is a deployment time decision. And it's a config file. You don't have to write different code for cloud or premise. As long as you use the frameworks that are common to both, you're going to be in really good shape. And you'll get a great experience using .NET in the cloud, of course. But you'll also see scalability features from the cloud start integrating deeply into .NET and becoming available on premises. Now, the reality is some of those services that you wrote will have to be rewritten to scale. One example is you might see performance issues moving to the cloud. It turns out could be your workflow. Every incoming request might access that inventory table. So I've troubled you enough about inventory, but you get the idea. The principle here is that scalability is contagious. It's kind of another form of Amdahl's law, if you're familiar with that. Basically, the least scalable part of the system is going to end up being a bottleneck to the rest. And that's something you need to think about when building these services. So given that, I've written down some rules of thumb to help you think about how to write services and design services today that'll scale out in the future. So even if all you need today is a single machine service, if you follow these patterns, you'll have to rewrite a whole lot less later. Now, a lot of this is going to be familiar to you if you've read the principles of service-oriented architecture, of SOA. It's largely the same thing. And that's because building services today using the SOA principles is a really great way to start building scalable services. So first rule of thumb, choose a high-level framework. I actually just mentioned this. So it's going to make it easier for you to retarget your code onto these scalable frameworks. Obvious examples, ASP.NET, Workflow, Windows Communication Foundation, WCF. Keep your service code separate from the code that you write that actually handles all the hosting stuff. Again, it's pretty obvious. You may want to change your hosting choices in the future, so it makes sense to cleanly separate things out. This needs a few exclamation points, actually. So partition. You want to build your application around these vertical silos. Silos that process requests, do some work, update some state, and return, while not interacting with each other at all. So the thought experiment here is ask yourself, what would happen if each request, each silo, happened to be hosted and running on a different machine or even in a different process? Would your program keep running? If not, why not? How hard would it be to do? That's actually a really useful experiment because even inside a single process, it turns out if you build your systems like this, you actually get really great multi-threading, does a really good job of optimizing your code for multi-core systems. So that's good. You also want to partition your application into tiers, even if they're just separate classes. You want to think about a communications tier that handles all the messaging and security infrastructure. You want to think about a logic tier that implements those vertical silos. And you want to think about your storage tier. And actually think carefully about it, because you want to design it to be partitioned up front. So think about your schema. Think about how your code uses the data. Think about those joins that you have. Think about what lines you could draw inside of your schema so that the data could be separated out. What cross-row dependencies do you have? What cross-row row and table dependencies? What consistency requirements do you have? What do you assume about one piece of data and another piece of data? And so draw the lines through which your schema can be partitioned while remaining correct. You'll find, for example, this is the same pattern that SQL data services, that SDS gives you. The user actually has to start drawing those lines. And then SDS is a great partition database engine. It'll take those lines. It'll scale them out for you. But you have to give it a hint, or else it can't do it. So more stuff. Use loose coupling. I've talked about this. So you want to build services that are built up of smaller composable services. You want the communication between them to be loosely coupled. And you want isolated failure domains. You also want to apply these concepts, of course, when you have services that cross-talk, that talk to each other. And of course, in today's world, every service talks to another service, and it's going to use loosely coupled messaging. You want to use caches and stale data. This is another thing that's really important. So a large percentage of the data that you access, even if you're going straight to the database, it's fine. But a large percentage of the data that you access should be able to tolerate cached or stale data. And that's where you need to apply the same analysis that we applied with the inventory table. Could I tolerate stale data? Could I tolerate inconsistent state? If you rely on synchronized reads and writes for all of your state, turns out you're creating a bottleneck. And so this is just a think hard kind of thing. Think hard about whether you want that bottleneck, whether you need it, whether it's essential to your program. Because if you have a lot of those, you may not scale terribly well. Here's another interesting one. Have just a few simple recovery paths. So this is a bit of this is recovery-oriented computing again. You want your software to self-monitor, to fail fast and fail safe, and also to recover quickly, because that's the other part of the equation. So you should expect, like we were saying earlier, that at any point in time, your process could crash. Even if your code is perfect, your process could crash. Your OS could crash. Even if our code is perfect, the OS could still crash. Turns out you could have bad memory. Pointer could change. It could dereference something that isn't there. Take down the whole machine if it's in the kernel. Also, even if all the software and all the hardware is perfect, turns out machines depend on something really important, the electric grid. You might have the power go out, and so your machine goes down. And all of these things, the process dying, the OS dying, the power going out, all these things are virtually identical, indistinguishable to the application. It's just stopping at any point in time. And so you need to think about how would you make it business as usual to fail at any time and then to recover gracefully from that. So once you have that, you can then start thinking about what other shutdown paths do I have? What other failure paths do I have? The more you have that nicely tested, stop at any time, recover quickly, you have that. Turns out every other error in your program, every other reason for shutting down, you can just reuse that code path. So this is another idea that's actually kind of old as the hills, scalability. It wasn't invented for scalability. So I used to work on the Windows Transaction Manager, MSDTC. And it turns out we used to use exactly this same technique. We had to assume, because the Transaction Manager is a provider of consistency, we had to assume that we could stop and be killed at any point in time, either the process being killed, the OS going down, whatever. And we had to remain consistent. So we'd write checkpoints in our logs and so forth. Every time we'd start up, we'd go back to the logs, read the data, recover all the transactions that were in flight, abort them if we could. But it turned out we didn't have a graceful shutdown path at all, because we didn't need one. We'd already implemented the quick one, the quick recovery one. And so when you do a net stop on MSDTC, it just terminates process. It really doesn't do anything else. It doesn't flush file buffers, doesn't write any clean log checkpoints. It doesn't really do anything at all. It just exits process. And that's by design. Mainly because we couldn't test it. It turns out in reality, 99% of the time, MSDTC doesn't stop because of a net stop. It's because something crashed, or the OS went down, or the power went out. Otherwise, it's just running and running and running. And so why would we spend time investing in code and testing something that would never get run? So we didn't. Lastly, be topology independent. So don't hard code anything that your administrator could legitimately change. And your administrator could legitimately change a lot of things. Could change machines, machine names, addresses, network topologies. So even putting addresses in config files, for example, it's what we do. We don't hard code addresses. They're in config files, right? Well, even putting addresses in config files at scale, it turns out that's a lot of config files to go out and change when something changes, when a new machine comes in, has a new name. And so there's a technology you can actually evaluate to address this in .NET 4.0, which is the discovery framework. What it lets you do is it lets you, in your code, find service addresses at runtime just by going and probing and going and finding services without needing to change any configuration. So that's a really useful building block to start thinking about how to build systems that behave this way. So that's the application developer's experience of scale. There's some stuff to think about, obviously. There's some new concepts. But really, scalability at this level, it's about leveraging the things you know, the things you've read, probably the things you're already doing in a lot of cases, the knowledge you have and the tools that you already have. So with that, I'll move on to the routing and data overlay. So as you've seen, there's some interesting challenges to scaling out services, infrastructure services. And actually, most of the interesting ones, the hardest ones, tend to show up in three particular areas. There's partitioning, there's routing, and there's state management. And you've seen this show up already in the workflow service example that I gave you. So there's two questions that really come up again and again when you're designing these scalable services. The first is, how do I ensure that requests that come in are processed at the right place, at the right location? And the answer, as we saw with workflow, typically involves partitioning and routing. Second question is, how do I manage state inside of my service? Now, of course, the invariant here is you partition your storage tier. That's what you always do. But for certain topologies and certain services, you may also want to partition your logic tier. Workflow is actually a great example of this. And you may want to cache or store transient data in the logic tier to get that processing locality that we talked about. So as we were building cloud services across Azure, we realized that what we needed here was a systematic approach to addressing these questions. And so what did we do? We built a framework. We built a framework called the Routing and Data Overlay that would do just that. And so in the future, you're going to see this technology show up inside of the .NET framework, really for both infrastructure developers and for application developers. And so what does the overlay give us? Well, first of all, we get a messaging model for partitioning and routing inside of a tier. And so what the service can do is it can directly send messages to specific partitions without needing to know any physical endpoint. And what that lets the service do is it lets it assign work items into partitions just by using a service-specific mapping function and sending a message. Secondly, we needed availability. And we needed to let the administrator make changes inside of the data center without the software being affected at all. And so when a machine is added or removed or it fails, the overlay gives us automatic detection, recovery, and repartitioning of those work items. And it actually gives them to the service for free. The service doesn't need to do anything. Thirdly, we needed a way to partition and store transient state inside of the logic tier. And it turns out the data overlay provides pretty much exactly what you'd expect. It provides a partitioned, replicated store for transient state. So we use all these features inside a number of services. We also use them inside of workflow. And I'll explain the technology first, and then I'll show you how workflow uses it. So the routing overlay is essentially, it's a structured peer-to-peer network. I've drawn 6 nodes here just to keep things more or less readable. You can imagine there could be many more nodes inside of an overlay network, of course. Now, each node here is hosting an instance of the service. They're all identical to each other. They're all pretty much clones. And you can think of each node here as being a machine. It could also be a virtual machine. It could be a process. But just to keep it simple, I'll talk about nodes. Now, the routing overlay, as you can see, it's organized like a ring, like a doubly. What it is a doubly linked list that's joined at the edges. It gives us a ring topology. And each node maintains a routing table of all of the nodes that it knows about. There isn't full knowledge inside this system. A node will know all about its immediate neighbors, obviously, because that's how it joined. It'll have some good knowledge about the surrounding neighborhood, the nodes around it. And it'll have some limited knowledge of the space beyond, way on the other side of the ring. So what the ring is, essentially, is an addressing model over a partitioned virtual address space. So you can see the 0 to the 2 to the 128. We have an address space, 128 bits. What that gives us is 2 to the 128 virtual numbers, virtual partitions. So each node owns a range of partitions inside of this address space. Now each node has, each node has an identifier of its own. And it turns out the ring is sorted by node identifiers. there's a protocol for joining the ring where essentially a new node will insert itself into the ring between the two nodes that have the closest ID to its own. So the ring stays sorted as nodes join into part. Now, I told you that the address space is divided up among all of the nodes in the ring. Now, how that works is actually really simple. A given partition, which is identified by a number, is owned by the node whose identifier is closest to the node's identifier. So it's actually just simple arithmetic to figure out who owns what. So a node joins a ring. It'll claim the range of address space that's now closest to it inside of the overlay network. And so what this gives the service is a way to think about addressing partitions by number and then spreading them out, load balancing them across a set of machines. So that's kind of cool, but what do we do with it? Well, we do messaging, of course. And so the overlay, it uses the ring to provide a messaging model on top of those virtual partitions, on top of the virtual address space. The service sees the ring. The abstraction that the ring provides is that of a Windows Communication Foundation, a WCF channel. Sending on the channel, it sends a message into the ring. And receiving from the channel, well, it pumps a message out of the ring. It's what you would expect. The overlay is also built on WCF, and so it uses the standard TCP binding to send messages to those nodes that are close to each other and connected. So what can a service do here? Well, the service can send messages to those logical partitions, to those numbers. Now, literally, the to address on a message that's sent into the ring is just a number. It's just the ID of a partition. So each node is going to route messages, a message that it receives, to the node in its routing table that has the closest identifier to the to address, to the target. And this just repeats and repeats, hopefully not too many times, until the right node receives the message. So essentially, this is binary search across the ring. So the intuition you can get is that messages are going to be routed in log n time from one point to another, even at the farthest points. So here I'll show you a message being routed. Takes a few hops. So we've targeted this message at ID 4601. It bounces around a little bit. You can imagine there's other nodes here. They're spread out. And finally, it arrives at the node that has the closest identifier to 4601, which is 5000 here in this example. And so what this lets the service do is it lets the service affinitize requests by deterministically mapping some input that's consistent across a set of multiple requests to the same partition inside of the ring. And so now the service can send messages to partitions. But what about availability? What happens when nodes fail? So the routing overlay also provides dynamic reconfiguration. The IT pro can add machines, put them in the ring, can remove machines from the ring, or machines can just kind of fail on their own. And nodes will be monitoring their immediate neighbors. And what they'll do is they'll take steps to heal the ring when something goes wrong. And this is what we call an elastic host environment. A ring can shrink all the way down to one node, and the service is still running, actually doesn't notice. It can also grow to hundreds or thousands of nodes. And all this can happen without, again, the service noticing or even being disturbed. So in this example, I'm going to take down node 5000. So the address space that 5000 used to claim gets kind of divided up. You can see it's a little bit wider at the bottom. Gets divided up among its neighbors. So we're going to send another message to ID 4601, to partition 4601, and it gets routed. Turns out 5000 is down, so the message gets routed over to 5501. So every partition in that address space is always available at any point in time, even when the IT pro is busy taking machines down, adding more machines, changing things around. Machines can fail, and life goes on. The service remains available. And in fact, it doesn't even notice when machines are lost. And from outside the service, there's actually no sign. You're just sending messages in. You receive responses. There's no sign that a failure has actually happened inside the service. So that's the routing overlay. Now, I'll move on to the data overlay here. And what the data overlay is it's a piece of infrastructure that's built on top of the routing overlay. And of course, it assumes the peer-to-peer network that the routing overlay offers. What the data overlay does is it gives the service a transient state store. There we go. The service can use the transient state store to associate state, the state that it works on, with a specific partition. What the state does then is it follows the partition around. As the partition gets failed over between machines, load balanced around, the state will travel with it. And so the data overlay gives the service the ability to essentially ship functions, to ship messages to state. And there's no need for cross-machine I/O. We don't need to go to a third tier to fetch data at a given node. Basically, messages come in, they get routed to the node where the data lives, and that's where the data is processed. And so the state here is largely transient state. This wouldn't be enterprise state because there's no backup story or analytics or anything like that. Also, local storage can be used like a local disk, but the default is in memory. Now, each node has a local data store where it keeps instances of these data structures that we call entities. And that's kind of the atomic unit of storage for the data overlay. So I have 2 rows here in the table. Each one of those is an entity. And you'll notice they have a partition ID. And the partition ID isn't 5000, even though both of these entities belong to node 5000. That's because 5000 is currently the closest node to those partition IDs. And so when a message arrives at node 5000, the service code can then go and find entities that are related to the message. It can read and write their contents. The contents, the example here is, of course, a workflow instance queue. The contents are data structures. They can store more granular data. It can be a name-value pairs, for example. It can be a hash table or a dictionary. Now, what we can then do, so how does this work? I've represented the data here, the entities, as letters, just to keep things simple. And so here the service is going to receive a message. The message is targeted at node G. Or rather, it's related in some affinitized way to the state represented by entity G. And so just like with routing, we're going to do something to map that input to some partition. So we're going to run a hash function, let's say, and we're going to run it on G or something that signifies G, and we get 4601 as before. So then we route that message to partition 4601. It arrives at node 5000, which conveniently happens to be the node on the ring that stores G. And so that's how services can partition their transient state on the data overlay. So what happens when they go down? Well, the data overlay replicates state across nodes to provide availability and ensure that data survives over time. So remember that each entity has a partition ID, and it's stored at the closest node that happens to be closest to that partition ID at any point in time. We call that node the primary for any given entity. Now, the primary owns servicing read and write requests for that piece of state. It also owns determining when a write is succeeded. Now, entities are also replicated to secondaries. They're the next closest nodes to that ID. I think you can see it in the slide as little gray letters that are shadowed. So what we call the replica set is essentially the primary plus the number of secondaries. Here I've used a replica set size of 3 if you count. And really what that is a design time dial. It's something that the service coder would think about when designing the service. So what there is here is a trade-off between the safety of the data and the cost of storing data. The latency of writes, the overall system throughput to replicate state around, to synchronize data over time. And really what that represents is the number of simultaneous failures that can occur inside of a ring before data is actually or data can be lost. So what happens when a node fails? Well, let's take out node 5000 again. You're probably tired of seeing that. So now, it turns out G and H are in doubt. They need a new primary. So I'll blow things up a little bit so you can see it a bit better. Turns out node 5501 is going to become the primary. Let me click again. Sorry. Node 5501 is going to become the primary for G, and there's, of course, a new secondary for G off to the left. H had a different partition ID, so it actually goes the other way. It replicates, it becomes node 905, becomes the primary. And, of course, there's a new secondary stored over there. So now a new request comes in, and again, it's targeted at state G, so we'll run our familiar mapping function. Maps to 4601 yet again. Request gets routed inside the ring, and again, it lands at 5501, because node 5000 is kaput. And so the request arrives. It wants G. And it turns out the data is sitting right there, because 5501 is the new primary for G, and we can read and write our state, which is great. So how would a service actually use the overlay? So I'll go back to the workflow service again, and I'll show you what happens when it receives a message from the outside. Now, here we have a communications tier node receiving a message. So the node is going to run a partitioning function. It's going to route, again, just as before, it's going to route that message to the right place on the ring, and there it finds the data overlay. So it stores the message in a queue, and then starts pulling messages from the queue and processing work. Now, in this case, it turns out we have this completely open, this empty service instance. What I'm representing here is that we have no workflow state because we haven't loaded it yet. That was the first message. So we go to our third tier. We go to the storage tier, which is where the instance state is stored. We load the data in memory, and we start processing requests. So pull messages out of the queue. There might be a bunch at this point. Process the work, update instance state. Now messages may be arriving at this point in time. They get stored in the queue. They get processed again. We get the locality that we talked about. Eventually, the queue's empty, and we're done. So instance state gets stored back into the storage tier, which is SQL Data Services. And eventually, the state will idle out. And of course, we'll update our queue, and we're done. Now, again, as I said, the storage tier here is SQL Data Services, SDS. What SDS represents for us is it's a partitioned, scalable database. You know it as the cloud service, but we also use it internally for a set of services to actually be a scalable third tier. It's actually really, really useful in that role. So what did the workflow service get out of all this? Well, first, it got scalability because it partitioned out its logic tier, in this case by instance. And it did so in a way actually very, very reminiscent of what I showed you earlier in the slides. Messages come in, they get sent by a stateless communication tier to the right place in the logic tier, and they get processed. And they get processed repeatedly at the same node with the same memory. We also got locality, because by routing those requests to the right node, we found our message queues, we found our instance state, all stored at the same place. We also got availability, because even if machines fail, and I won't take down node 5000 again, but you get the idea. Even with failures, requests still get routed to the right place, which is where the state is stored, and the queues stay alive, they're failed over, they're still available, everything's good. So let's go back to those questions that I asked before I introduced the routing and data overlay. So again, how do I make sure that incoming requests are processed to the right place? Well, we partition on service-specific input. In the case of workflow, we partitioned on workflow instance state. Other services may have different choices, different ways of partitioning. And we use the overlay to route messages to specific partitions in this large address space with many partitions that gets load balanced pretty smoothly across the entire set of processing nodes. And we didn't need to know any physical addresses to do that. So the IT pro could come in and change things. We got seamless failover for those changes, for those failures. It all just works. Then how do we manage, so forgot my bullets. How do we manage state inside of a service? So across the board, we took a really hard look at our tolerance for data loss. And we did this really for every service, not just workflow. We thought about, again, could we lose this data? Could we loosen consistency on this data? Could we handle reading stale data? Could our program remain correct? What are our read-write patterns? How transient, how persistent is this data? And then we made some decisions. We used local caches in many cases. We stored transient data. In fact, the workflow message queues are entirely transient data. They come, they go, messages come in, they get processed really quickly. There's no need to store those in a database. There's really no need. So we stored them in the logic tier. And of course, we use technologies like the data overlay to get fault tolerance and availability, locality, all these things. And of course, where we had persistent data, what we did is we used a partition storage tier, which is the SDS service. And we used that to implement those partitions in an effective way. So, like I just said. So I've told you all about routing, partitioning, state management inside of a service. And I also took you on a deep dive into the framework technology that we've developed to facilitate our scale-out and facilitate building scalable services. And I've used workflow pretty consistently throughout as my example. So now I'm going to take a step back here, take a drink. And what I'll do is I'll give you a little bit of high-level insight into how some of the other services across Azure, how they scale out. So it's a little bit kind of around the platform in 3 slides. But what you'll see is that even where the individual bits, the underlying bits are different because they were built at different times, you'll see that virtually all of the same principles of scalability apply to each one of these services. So moving right along. So our first service is SQL Data Services. I've talked about it a little bit. What SDS is a partitioned, scalable database service. It's a public cloud service. And as I've mentioned, we also use it inside of our data centers as the storage tier for a number of our services. Now, unfortunately, SDS can't use itself as a storage tier because it doesn't exist. It's kind of like the last domino in that sense. And so what that means is that it has to solve, SDS has to solve what amounts to a set of really interesting hard problems that all of our other services don't have to solve because they can use SDS as the storage tier. So SDS is built using 2 tiers. There's a front end. It manages communication, speaks protocols, manages sessions and security, pretty much everything you'd expect. Then there's a back-end service. And what that does is it implements the business logic of being a scalable database, the database semantics. And what it does is it partitions out individual instances of the SQL engine. So tables and rows are partitioned by the application. I actually mentioned this earlier. Turns out the application is responsible in SDS for drawing the consistency boundaries that SDS then goes and enforces and load balances. And so partitioning ends up being a first-class concept for all of the applications that use SDS, including, of course, our services. The application needs to help SDS by drawing those consistency boundaries. So the back end of SDS is implemented using pretty much the same concepts as the data overlay. There's a peer-to-peer network. There's a fault-tolerant nodes. Storage is replicated. And of course, the consistency dial for this network and for the storage is really turned up to the max, because this is a layer where you really don't want to see stale data. You want to let the application decide when stale data occurs, but it's the responsibility of the database at a high level to be the truth, to be the authority, to provide that consistent data. And so the network underneath SDS, as I said, actually turns up consistency to the max. And they'll actually sacrifice some degree of availability to keep their data consistent. I don't know if you went to, I have a pointer at the bottom, if you went to Gopal's talk on SDS under the hood. Did any of you go to that? I missed it. It was good? Yeah, it's actually a really great talk. And there's some really interesting work, as you can see under here. So if you get a chance, you should go to microsoftpdc.com and check out that talk. And anyway, as I mentioned, the underlying technology here is a partitioned SQL engine. It's just the same SQL, but partitioned out. So moving on, there's the service bus. So you've probably gone to one of Clemen's talks. I know he had several. I actually went to a few. They were great talks. Again, you should go to the website and see them if you didn't. Now, what the service bus is, it's basically a communications technology. It's a communications service. And users establish sessions with the service bus. And they get bidirectional communication. They get firewall traversal. It actually doesn't sound like a whole lot. This is a really, really killer app, though. I would say it's probably, this is just my opinion, it's the service in Azure that probably does the most to enable new scenarios for software that you have today that's written to run on-premise. But getting this universal naming system, this universal connectivity, it's really just a killer app. Anyway, so users listen on names, and they can send messages to names. And it uses the service bus, the users use the service bus as the centralized name manager for kind of rendezvousing on these names. And so I'll give you a quick look into how the service bus scales from the inside. Really what that means is, how does it manage its state? That's the question you ask for every scalable service. So for the service bus, the state that it manages is really just the list of registered names. There's not a whole lot else in the system. Now, name lifetimes, it turns out they're bound to user connection lifetimes. When a user disconnects or a user goes down, reboots the machine, whatever, then essentially the service bus will delete that name, actually as quickly as it can, because the name is no longer available. And then the user comes back, reboots, runs a program again, and then it recreates the name. So what that means is that the authority for the data, really the truth as you'd think of it, is actually outside of the .NET Service Bus entirely. It's at the user's side. And what that means is that the service bus today actually doesn't need to persist any of its data. So it doesn't have to use a database for anything. Turns out the third tier, as you can see there, it's actually a composable service. We call it the naming service. And it's partitioned by the obvious pivot, which is by user. It turns out each user gets his own tree of names, his or her own tree of names. You can create hierarchical names, so it looks like a tree. And what the naming service does is it uses the data overlay to partition and scale out the whole forest of trees across the naming service ring. So you can think about the naming service as a bit of it's like this big scalable cache. It replicates data across nodes, so it's not going to lose state just randomly. Even if it did, though, even if state were lost, the worst case is exactly the same as if a connectivity node went down, which is the user gets kind of a disconnection and needs to reconnect. And you can handle that even at the software layer. You don't have to even let the user know. And so the user is the authority for the system. The service bus can take advantage of that to store all of its data in memory, scale out really broadly, partition really broadly, be really fast, really scalable, and really available. So this is a great example, actually, of taking a look at your state management algorithms and really figuring out where can you relax your consistency requirements? Where can you relax the need for persistent data for exactly once, for the truth? So the next service, live services. So the mesh, you've probably seen all the keynotes and all the talks. It's another really great technology. What it does is it gives you location-independent access to your data, and it synchronizes data everywhere between devices, PCs, other things. So how's it built? How does it actually scale? It turns out that the mesh has, well, it has a stateless front end, mostly handles user connections, authentication, some degree of redirection at times. And the logic tier, it represents the actual live services. So there's accounts, notification, and presence. All those services are pretty much independent of each other, but they share the same user state. And so they share state down below in the storage tier. So there's partitioning at each layer. In fact, the URL that the client software uses to send a request and actually connect to those front-end machines, that varies per service. It's a different URL. So that's already a form of partitioning. Inside the logic tier, which as you can see is obviously partitioned kind of along service lines, there's individual pools of machines for each service. Individual nodes are largely stateless, and the storage tier is used as an authority for all the data. That said, almost all of the data access inside of the mesh is actually through caches. There's pervasive caching throughout the system. It uses the REST model, which is it's actually just the HTTP 1.1 model, where the user can specify to what extent they want stale data, cache data within what tolerance. And so because the truth is expensive, the mesh at the level of the services uses cache data pretty much wherever it can. User account information is actually a pretty good example of that. Changes pretty infrequently. So it turns out just about every node in that tier is going to have kind of a cached copy of that data. It'll expire it over time, but it really doesn't need to go to the database every time to fetch it. Now the storage tier itself, you can see, is kind of divided into these two little boxes. Turns out one of those is the persistent storage tier, and one is the transient storage tier. And what this means is that the service developer, if you're developing one of those little account services or something like that, you need to make a decision up front. You need to think hard about your state. Do I store it in the persistent store? Do I store it in the transient store? Make that decision up front because you've thought about your data and you've thought about what kind of tolerance you have, how long your data lives, and so forth. So again, you're seeing all the same patterns and principles. There's again eventual consistency. There's partitions. There's transient data, and of course there's pervasive caching. So at this point, I'm going to take a step back, and I'm going to show you a bit of what we gained from building scalable services. I mean, aside from the obvious, we got the ability to tolerate lots of load. We have the ability to be available at all times. But what else happened? So as we were building scalable services, we discovered what we call the virtuous cycle of scalability. And so first, we designed our software to run on multiple machines to scale out. So we followed all of the principles of scalability that you can see here. From the software perspective, what this then let us do is it let us embrace a new operations model. So again, from the software perspective, we could start treating our machines, each individual machine, as a disposable item, kind of like a paper plate. That's the metaphor we tend to use. So when something malfunctions, as I said before, we can simply remove that machine from the service. We can replace instead of repairing. And what this operations model lets us do then is it lets us build our systems on really cheap commodity hardware. Now, over time, this is going to lower the cost of capital, the cost of the machines. It'll lower the operations cost. It'll also lower the cost, even the cost of electricity, the watts that we consume per CPU cycle. And it'll let us be a lot more efficient in that respect. And so having done this, we then come back to the beginning of the cycle. We can take our software to the next level. We can get even greater efficiency out of our operations model. And then we can buy more machines, support more users, rinse and repeat. So I'll spend a couple more minutes on the operations model, something that we call 24/7 lights out. So again, the key here is to have the software and the operations staff treat the machines that we have, the hardware that we have, as disposable. So we turn machines off and we replace them instead of repairing them. We don't diagnose and repair anything inside of the critical failure path for a service. When something goes wrong, the pager goes off, you yank the machine. That's all you do. And so when we're operating a service, we don't give our machines any individualized attention. We couldn't. We have way too many machines for that. And so if we have to know a machine's name, if we have to debug it, terminal server into it, gather any individual log, we're probably doing the wrong thing. So I do want to note, by the way, when I talk about replacing machines, or that machines are paper plates and they're disposable. It's not that we have this huge pile of garbage outside of our data centers. The key is really to avoid doing your diagnostics and repair while the service is active and everyone's all in a panic and you're waiting for things to get fixed. Instead, you just turn off the machine, stay calm, take it outside. And of course, at that point, there's lots of repair options, recycling options, even if the machine can't be repaired. And of course, we're totally committed to being green about all this. So at the software level, what you're seeing here is a trend towards self-monitoring and self-healing systems. And I've showed you some examples of this with the routing overlay and the data overlay. And what this design gives us is it really gives us a simpler way to deploy and manage machines at this large scale. It also empowers the operations staff to be much more productive and to manage many more machines per person. So I'll wrap all this up. So recap, I've given you a look, I think, at some of the highly scalable services that we've built. It's pretty clear that scalability is one of the key attributes of software plus services. In my opinion, it's actually the key attribute. Scalability is contagious. I've told you this already. And we're moving towards a world of really pervasive connectivity. Services are ubiquitous. There's millions of users. There's billions of users. And really, Metcalfe's law, the law that says that the value of the network is the square of the number of users, that law is really taking hold. And we're starting to see, in fact, we've started to see for a while, that loose coupling and eventual consistency are patterns everywhere. So applications that work in this, to work in this world, in this ecosystem, applications don't need to change dramatically, but they do need to evolve and think about things and adapt. And of course, they do that by following the principles of scalability that we've talked about. You can build scalable services today. So we use pretty much the same frameworks, the same tools that you have available yourself to build services. We built on Server 2008. We built on Hyper-V. We built on .NET, on WCF, on the workflow, on SQL Server, many other technologies. Sure, we have some new things, some innovations across Azure, but we're working really hard to make sure that those get reflected back into the premise offerings that we have. And so as long as you're following the principles of scalability to build your apps, you can actually do really well today with what you have. At the same time, our platform's evolving. And so along the way, we built, as I've showed you, we've built some really useful technology on top of our frameworks. And we're framework builders. It's kind of what we do. And so we built the overlay, for example, as a really general purpose technology. So you should expect to see that technology integrate into the .NET platform and start underlying some of the frameworks that I've mentioned. It'll underlie future versions of the Windows Communication Foundation. It'll underlie future versions of workflow and help them scale better. And so what you'll see is that the same programming models that you have available today are going to evolve to offer scalability by default. So call to action, pretty obvious. Use the services. They're really great. Start thinking about composing them with your own applications. And of course, scalability will become contagious. So your apps will have to be scalable too. Develop scalable services and follow the principles of scalability along the way. Send us your feedback on the services, but also on what you need from the platform and the framework in order to build your own services at scale. And with that, please send feedback. You may have a plane to catch, but just take a second and fill out the feedback form, and we'll take some Q&A. Thanks. Oh, sorry. Yeah, sorry about that. If you're going to ask questions, you should really use the microphones. Line up at the. I think there's one over there. I don't see one on the other side. Actually, yeah, there's two. So let's get organized here.
Do you want to answer your question, or?
Yeah. Actually, you probably got there first. So.
Yeah, the routing piece that you mentioned. How and when is that being delivered?
So you should expect to see that after .NET 4. Yeah, actually, John, could you turn on that mic?
So that'll be out of band for .NET 4, or is that out of band for like 2008?
It's actually not clear yet. So certainly after .NET 4, the team that's working on this, we're very concentrated on building out the framework for the services at the moment. So we're focused on that. But we're very committed to getting this into the framework. So 4.5, 5.0, whatever the next plans are.
Okay.
So. Yeah,
Well,
switch over.
that actually answered my question, but you said something about you want to make it so there's consistency between on-premises development and, I guess, the cloud development, which would be the Azure platform. So you're saying that you can make an application that conforms to Azure conventions and uses Azure services and run it on premises, and then as you need the scale of the Azure cloud, you just port it to.
Yeah, so there's a word
Microsoft.
that Chris and Don used in their keynote, which was nascent, and I think that applies to this concept as well.
Okay.
Really what we're talking about is there's an aspiration that we have, which is that as long as you're conforming to a set of guidelines, following the right principles and so forth, obviously things do change between the cloud and the premise, but as long as you're doing the right things, you should be able to not have to choose up front where that program is actually going to be deployed. You should be able to write a program that can run on-premise and on the cloud. That said, as of today, we're just getting started in offering you hosting environments in the cloud. And so there's differences, there's limitations. Workflow, for example, I think today it doesn't support running like C# code running assemblies. I imagine we'll do that eventually. But you get the idea. It's really a question of time. And so that's one of the principles that we're following when thinking about how to differentiate cloud and premise, is make sure that the developer experience is unified. And that's just a given.
Cool. Thanks.
Yep. Over there.
Any thoughts on how a catastrophic failure would be handled? For example, everything that had node G in it was in one data center, and that data center got hit by an asteroid.
Yep, that could happen. Or even easier, the power could go out to the whole data center. Right?
Yeah.
Yeah, so the way we tend to think about this is if you need something like geodistribution, you can easily do node allocation that will interleave nodes. There's actually, now that I think of it, I think the Dynamo paper, Amazon's Dynamo paper, uses very similar technology. It's actually really cool to see all the validation that we get for this kind of technology across the industry. But if you read that paper, you'll see what they do is they interleave nodes so that when the replication occurs and when success is returned to the user, it ensures that the data has actually been preserved in remote places that couldn't be taken down by, say, a single generator going down. So similar idea.
Okay.
I was wondering what the relationship is between the overlays and Project Velocity. Conceptually, they seem a lot alike.
Yeah, there's some similarities. So Velocity is a third-party service. It's not something that runs co-located with your application. Now, it turns out Velocity, the way they relate is Velocity is built on precisely the same kind of technology. So if you think about how you would build a service that was a caching service, you would very easily build it on top of a framework just like this. And actually, that's what Velocity's done.
So they're using the overlays internally? Or?
They're using the same concepts, yes.
Okay, just the concepts, not the shared code?
Yeah, I mean, there's a set of instances of this code base, and they're using one of that. So,
thank you.
Yep. So, any other questions? I don't think we have swag for people who ask questions. No? Guess not. Yeah, next time. So, great. Well, thank you very much.